So we've talked about electric field, we talked about electric potential energy, we've talked about potential, just potential, V. And then we put electric field and electric potential together with calculus last time. So now I want to remind you about conductors. If you have a solid conductor, pretend that's a sphere, and it is charged, you know several things. One, the electric field is 0 inside the material of the conductor because all the charge is on the surface. And because this is a very simple single conductor, all the charge is on the outside surface specifically. Now, this means the electric field at the surface must be perpendicular because, so let me just draw it. Let's say it wasn't perpendicular to the surface. That one wasn't very perpendicular. If it wasn't perpendicular to the surface, there would be a component that would cause a charge to move. And this conductor has reached electrostatic equilibrium. Should have said that first. But if it's in equilibrium, the charges are not moving. So the electric field has to be perpendicular to the surface. If it wasn't, they'd move. So then they're not in equilibrium, so we haven't met our starting conditions. So once they're in equilibrium, the electric field is perpendicular to the surface. Now, let's go back to this electric field as 0 inside the material. So if we go inside here, we can apply our new equation that potential difference is equal to the negative integral of the electric field. Well, if this is 0, how do we integrate 0? So integrating 0 means that this is just plus c. It's a constant. So you can make up a number here. Let's say it's 3, maybe 5, 12. Because whatever this number is, whatever this constant is, when you take the derivative of it, to go back to E is negative derivative of potential. If you take the derivative of 12, it's 0. Derivative of 50 is 0. So the integral of 0 is a constant. So everywhere on the surface and inside the conductor is the same potential. Everywhere. Everywhere is at the exact same potential. So if the outside surface is 15 volts, there's 15 volts, that's 15 volts, that's 15 volts, that's 15 volts, that's 15 volts. Now outside it decreases. And you know for a spherical shape like this, you'd use V equals KQ over R. So the potential decreases as you go away from it. So this leads us to a new term, the other one in the title of this, which is no longer on the screen, the word equipotential. Equipotential, said quickly enough. Equipotential means equal potential, or same V, because potential is V. So an equipotential surface is the same potential everywhere. So first example of this, I'm going to have 2 parallel plates of charge, and this one's positive, and this one's negative, and they're not on the screen, so let me slide it up before I continue the picture. So, and why are they charged? Because we hooked up a battery to them. And this battery, to make things nice and simple, is a 10-volt battery. We have also grounded this side. So this side is at 0 volts, okay? And that means this side is higher by 10, so this is 10 volts. Now we know the electric field in between. Electric field always points from positive to negative because it shows what would happen to an imaginary positive particle. So the electric field goes straight across. And you could calculate this field. A uniform electric field, we take our derivative equation and we turn it into just a delta equation. What's the potential difference between the two sides, 10 volts, divided by what's the distance between the two sides? And so that would be a number given in the problem. But I want to talk about the equipotentials. So if this is 10 volts, we have, and we need to get down to 0 volts, that means someplace is 8 volts. Well, wherever it is on 8 volts, it's going to steadily decrease. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Because it's a uniform field. That's what we're starting with our simple case. So 8 volts is here. 6 volts is here. 4 volts is here. And 2 volts is here. And these should be, to the best of my ability, evenly spaced. Because if we're going down this staircase, we're decreasing in voltage as we go along the electric field line. We go down 2 volts, and they go down another 2 volts, another 2 volts in the same spacing, because this is a uniform field. But the big thing I want you to get out of this is that the E field lines and the equipotentials are perpendicular to each other. For the next case, I'm going to do the opposite. So let me turn the page. And I did this one on the computer, so it would be accurate. So here is a, let's see, that's not on the screen. This is a 1 nanocoulomb charge in the middle, and it's a positive charge. And I used a program to sketch out the equipotentials. I did this, or the program did this, because they said, okay, this is a point charge, so V is KQ over R. So if I invert this equation, R equals KQ over V. So we could make a little table here. If I want to find potential in volts, if I want to find the radius for each of these equipotentials, I can put, I'm going to look for 40, 30, 20, and 10. So this is 1 nanocoulomb. 1 nanocoulomb, and it's positive. So 9 times 10 to the 9th times 1 divided by V of 40, I get a radius of 0.225 meters. 30 volts occurs at 0.3 meters. 20 volts occurs at 0.45 meters, and 10 occurs at 0.9. You can verify those if you want. One of the features I want you to notice is I keep referring to radius because this point charge is going to make an electric field everywhere around it, and a scalar field, a potential field everywhere around it that's spherically symmetric. So if I calculate this distance, it's that distance in every direction has the same voltage, so the equipotential. I also want you to notice these are not equally spaced. 40 and 30, that's only 0.075 apart. But 30 and 20 volts are 0.15 apart, and 20 and 10 volts are 0.45 apart. So this shows I actually did more on the program, but 40, 35, 30, 25, 20, 15, 10, and 5. And you can see as I decrease in voltage by the same amount, each of these drawings is 5 volts apart, it gets farther and farther away. This is because, let's draw the electric field. We know the electric field from a positive point charge points straight out. Straight out, straight out, straight out. The lines, the electric field lines are closer together here. It's a stronger electric field, and so it's also a stronger location of potential. Out here, the electric field's weaker. The field lines are farther apart. So since potential is the integral, how fast is the electric field changing? Actually, electric field is how fast is the potential changing. It gets weaker as you go farther apart. Again, I want you to notice they're perpendicular. The electric field comes straight out from the center, and the equipotentials are circles around that. So these are always meeting. Oh, I didn't do a good job on that one, did I? These are always meeting at right angles. So I have another picture, it's a little more interesting. So here I have a positive charge and a negative charge. And first, notice that the electric field, when it's close to one charge, it's pretty much a circle again. But as it gets away, it's less and less a circle. Like notice how this one is kind of squished in and spread out on the far side here, because these are the equipotentials for both charges together. This line in the middle, and because these are each 1 nanocoulomb, so positive 1 and negative 1 nanocoulomb, this is the same distance from both of them, so the potential is 0 right here. And it's 0 everywhere along that line between them. So if I draw the electric field, I know it's got to go from positive to negative, so I go straight across. Well, now I don't just want to sketch in the curves, I want to sketch in the right curves. And I can use my equipotentials to do that. I need to leave this one perpendicular to the surface, and I make sure I cross each one perpendicular, which means I'm needing to turn. So I always hit it perpendicular. Oops, I didn't turn enough. There we go. So before, when I did these, I just sketched out any old random curve in between there. But now I know exactly the right curve, because my line has to leave perpendicular to the surface, and it has to hit each one of these perpendicularly. So this one has ended up being lower than the other one because I left it a slightly different angle, and I'm following my perpendicular stuff. And it works out here. Would leave, and I do have to curve some because I've got to make sure I hit perpendicular. Equipotentials and electric field lines are always perpendicular to each other. I'm going to trace this one backwards because I find it easiest to go where the lines are bunched together, but then I know it goes this way. And then one more. Let's go out here. So again, not only is it perpendicular, but also notice the direction. You know they go from positive to negative. Well, the closest equipotential to this is positive 30 volts. At the end, the closest is negative 30 volts. So electric field lines point from positive charges to negative charges, or electric field lines point from high potential to low potential. You are going to be doing some drawings like this. And it's a good thing I just finished because y'all are about to walk in.